Chapter 12, Deflection of Beams and Shafts. Example number 10, Solution 2. So we already have solved this question in a conventional method, which was a derivation of elastic curve equation from moment, then integrated twice to get the deflection. But this time we want to solve it in an easier approach, which is just considering, for example, because there is a 1 degree of indeterminacy at the structure. So if we consider just, for example, a moment at A, so as a redundant moment, and then replace it back again. So let's see how that goes. So one can say in solution 2, consider moment at A as a redundant moment. So the entire beam or the original beam can be replaced by two beams. First, a two simple support beam with a concentrated load of W, a plus a two simple support beam with no loading and the effect of moments. So we just translate the uh, fix end moment by a uh, concentrated moment and just uh, divide the beam uh, in a case that we have, instead of the original beam, we have two beam, two simple support beam, which is far easier to analyze, and apply the effect of fix end moment at a two simple support beam here. So let's see how that goes. So, and that's also the effect of superposition. If we call them 1 and 2, so the first one is a two simple support beam with a uniformly distributed load of W. And if you want to calculate tangential deviation of B with respect to A, that's A times, and A in this area, times L over 2, which is the half of the length of the beam. Mhm. So, and if you do so, it just gives you a TB with respect to A is WL to the fourth over 24 EI. Mhm. And if you do the same for the second beam, it just says uh, it just goes down in the M over EI with the amount of MA over EA. And if you calculate T with respect uh, to A, this time for the moment, it just says A2, and this is A2, times 2/3 of L, which is the distance to the B. And that's a negative, because the area is negative, a 1 over 2. We don't know what MA is, and that's a negative MA L squared over 3EA if you do the math. And then what? It just says with the effect of superposition, even if you want to draw the tangential deviation of B with respect to A, that goes to two scenarios. The first one is for the effect of W, and the other is the effect of moment. The effect of moment just create a deflected beam like this, and the effect of W goes like this. So that's the T tangential of B with respect to A for W, and that's tangential of B with respect to A for M. And then what? And we already calculate their effects separately. And at the same time, we do know TBA, tangential deviation of B with respect to A for the entire B is 0. And how that goes, that's like this, because it's a, if you consider the original beam, that's like a fix, it goes like this and comes back here. So if you draw a tangent to the B, that's a TB over A total, and that there is no change, there is no vertical flip-flop for that. And at the same time, we all from the superposition from the figure here, we already know what t b with respect to a is goes to two component. The first one is effect of w, and the second one is the effect of a concentrated moment at a. Mhm. And if you do the math, it just gives you the numeric value of, and both of them should go 0 because we already know that there is no change in tangential deviation from A to B or B to A. So that gives us MA is WL squared over 8. Mhm. And if you just simply replace that in the second configuration and just summation of moment about point A goes 0, it just gives us a MA in considering MA, but MA plus RB times L, RB times L, and that's MA, and that gives you RB, it's a negative MA over L. By negative, it just says the direction of RB was downward. It was not consistent with our direction. And RA is just should cancel out RB, and that's a positive WL over 8 for the second figure. And what if you again come back to the original shape, which says, for example, RA reaction at A for the original beam is the reaction of what? Of the reaction at A for the original beam, which is the reaction at A total, it just is equal to RA reaction at A due to W, which is W is here, plus a RA of concentrated moment at A, which is this one. And we already know to how to do that, calculate that, then that's RAW plus RA moment, and that's a half of WL for the first scenario and 1 over 8 WL from the second one, and that gives us a 5 over 8 WL for RA for the original beam. So that says if the RA is 5 over 8, the other one goes by 3 over 8. So that's RB. And at the same time, if we want to know what is the theta, we already calculated reaction at A, reaction at B, and we want to know what the theta at B is. So theta of B with respect to A is just theta B minus theta A. And because the original shape has a fix, there is no theta A that goes by 0, then theta B is just m over EI due to weight, distributed weight, plus m over EI due to concentrated moment. So if you do the math, the first part m over EI due to the distributed weight, it just gives us WL cubed over 12. And that's the second part is just a m over EI due to m, and that's a negative WL cubed over 16. So if you add them up together, 1 over 12, a negative 1 over 16, it gives you WL cubed times 48 EI, which is exactly the amount which we calculate in conventional method due to integration. So that gives us a RA is equal to 5 over 8 WL. RB is 3A over 8 WL, and theta at A is equal to 0 because that's a fixed support, and theta at B it goes by a WL cubed over 48 EI. That's uh, what, what we exactly calculate in a previous example. In next video, we'll solve it with a third method, which is a effect of considering the redundant reaction at support B. Let's see. We'll review that. Thank you.